Hi guys, welcome to NetGate Chemistry. So in the previous video of quantum chemistry, we have discussed about the postulates of quantum mechanics. So in this video, we are going to discuss about the Schrodinger wave equation. So the first Schrodinger wave equation which we are going to discuss is the time-independent Schrodinger wave equation. So we have this equation h of psi is equals to E of psi, right? Here h is the Hamiltonian operator for the energy E, right? Now value of Hamiltonian, we know that it is equals to minus of h cross square by 2m del square plus v. This is the value for Hamiltonian. Now what we are going to do is we are going to put this value of Hamiltonian in the equation. So what we are going to get is minus h cross square by 2m del square plus v whole into psi equals to E of psi. Now if I open this bracket and divide the equation with h cross square, what I am going to get is del square psi plus 2m by h cross square E minus v into psi equals to 0. This is after rearrangement as well, right? What I have done is I have taken this E psi into left hand side. I have divided the whole equation by h cross square, and after rearrangement I have got this equation, right? So now this equation for Schrodinger wave equation is for 3 dimensions, right? If we want to change it into 3 dimensions, then this value of del square will be replaced by this one, right? So when we put value of del square as this in this equation, what I'm going to get, now this particular equation, or you can say this equation, these are the equations for time independent Schrodinger wave equation. Now you also know that value of h cross is h by 2 pi, right? So when we are going to put this value of h square here, so what we are going to get is, we are going to put this here, so we will be getting del square psi is equals to 8 pi square m by h square E minus v into psi is equals to 0, right? So these are simply the rearrangements. What you should know is that this is an equation, right? Using eigenvalue equation we have derived this. So what we have got is we have used an operator H operator which is for corresponding observable E, right? For energy observable we use Hamiltonian operator, and the value of this Hamiltonian operator is this, okay? And then after rearrangement, after putting this value of Hamiltonian in this equation and after rearrangement we get this equation. So after substituting values of del square we got this equation, and after substituting the value of h cross in this equation we got this equation. So these are simply the rearrangements, okay? So this is the time independent Schrodinger wave equation. Here you can observe that here the t observable is not coming anywhere, so it is independent of time. So now we are going to discuss time dependent Schrodinger wave equation. So now if we want to discuss about the time dependent Schrodinger wave equation, Now if we want to discuss about the time-dependent Schrodinger wave equation, then in that case we are going to use Hamiltonian having value iota h cross del by del t. So we will be having this equation just like in the previous case, h psi equals to e psi. In this case we are going to put the value of Hamiltonian as this one. So it will be iota h cross del by del t psi is equals to e of psi. I have just substituted the value of this Hamiltonian here. Now what I'm going to do is I need to do some of the rearrangements. Now it will be iota h cross del psi by del t is equals to e of psi. Now I will take this del psi LHS in the left hand side. I will take this psi also to the left hand side, so it will come in the denominator. Now e is here and I will take this iota h cross to the right hand side, it will come in the denominator, right? And this del t will also come here. So what I have done is I have simply separated the psi values and the remaining. So I have taken the del psi and psi onto the left hand side and the remaining values onto the right hand side. Now I will integrate both sides. Now integration of 1 by psi is equals to ln of psi. And here what we can do is I will multiply and divide numerator and denominator by iota. So in the numerator I will be having iota, in the denominator I will be having iota square, and you know the value of iota square is equals to -1. So here iota into iota will become iota square, that will be equals to -1. So I will simply take minus sign here. Now remaining values are h cross in the denominator, okay, e in the numerator, and what we are left with is del t. So here only variable left is del t, remaining are constants. So I will simply take this integration sign onto del t only. So here what we will get is ln of psi is equals to minus iota e upon h cross. Integration of del t is simply t. Now what we can do here is that if we want to take this ln onto the right hand side, then it will become e to the power, okay? Whenever ln is shifted to the other side, it becomes e to the power. So we will get psi is equals to e to the power minus iota et by h cross, right? So this will be the value of psi, okay? And this will be the time dependent Schrodinger wave equation. Here you can see that t is coming in the equation, so it is definitely dependent on the value of time. So what we have done here is that we have used this Hamiltonian in this equation, substituted and then separated the, so now I have taken this del psi and psi onto the left hand side and remaining values on the right hand side, and then integrated, and after integration and rearrangement we got the time dependent Schrodinger wave equation. So these are the time independent and time dependent Schrodinger wave equations. So now there are certain applications of Schrodinger wave equation as well, so that we will discuss now shortly. So that will take up only 1 to 2 minutes. Now we are going to only discuss what are the applications, and then we will go on to each of these applications and elaborate each of them. So right now we are just going to discuss what are the applications of it, okay? So the next topic is applications of Schrodinger wave equation. So basically there are 4 main applications of Schrodinger wave equation. First one being particle in a box, right, which is going to represent the translational motion. Second application will be hydrogen atom, which is going to represent the electronic motion. Third application will be rigid rotor, which is going to represent the rotational motion. And fourth application will be simple harmonic oscillator, which is going to represent the vibrational motion. So these are basically the four major applications of Schrodinger wave equation, and one by one we will be discussing each of them. So far you should know that these are the four major applications of Schrodinger wave equation, which we will be discussing in the upcoming videos. So I hope so far whatever we have discussed in the video you are clear with that. So far that's it for this video. Thank you so much for watching.